So I'm not going to go and waste any time with this because your time is valuable, and I want to make sure I get to answer the questions adequately for everybody. So here's your practice exam. I'm going to go ahead and go over basically everything in it. And I'll mention where it differs from the actual exam and how it will differ from the actual exam. Okay? So should be plenty prepared for that. There's 34 or 35 points of question. The final count on the actual exam, I think, is 35 points of coding. Three coding questions, 3 methods to write for coding. One is worth, each of the tree ones is worth 12, and the hash table one is worth, or the hash map one is worth 11, just so I could bring it up to 35. And again, while I didn't total it up over here to 105, it totals up to 105 in the actual exam. Also, the length of the exam, it's just simply because there's a lot of questions where I want you to draw things, so I give you plenty of space to draw and erase, right? So, all right. I will add in on the exam, the second page over here has the standard, here's what method strings have, here's what methods the tree has, although you shouldn't need to use them, and here are the methods that you need for a map, right? I didn't put delete for the map because you shouldn't have to delete anything for the map, okay? So let's get started. This first page over here, it is exactly the same as the page you'll get on the exam, with one caveat. On the exam, I have an additional sentence added here saying you may justify your answer with a single sentence, okay? You may justify your answer. Now, that's just simply so that if you, that's for situations where you might put linked list instead of stack or queue, and then you can justify, well, it's like the linked list, it will handle that, and more if we need it to. So, you know, because linked list can fulfill the role of both stacks and queues. But notice that heap isn't an option here, right? We have priority queue. Okay? So you need to model which patient should be seen next at a hospital. Patients should be seen in as close to order of arrival, but patients with a more severe situation should be seen first. So what kind of data structure would you use to model this? Priority queue. I heard it over there. I heard it over here. Right? This one's a priority queue. Right? This is like the example I use for a priority queue. All right? Now, on the other hand, a router needs to hold packets in a buffer and deal with them in the order they appear. Queue. That's a queue. Yes, that is also an example for a queue. This is one of the big uses for a queue, which is a buffer. Just things need to get scheduled, right, and to be taken care of, and then we deal with them in the order that they appeared of because that they appeared because that's fair. All right. What if you need to model a hierarchy? Yeah. Tree, I heard it there, tree. So tree, notice I just put tree rather than binary search tree so that you could, so you didn't have to think about that too much. You need a data structure to hold your previous decisions in case you need to backtrack. That's a stack, yeah. A classic wrong answer I have seen on this and in the final exam is somebody putting down recursion. That is wrong. The recursion is not a data structure. It's a technique, and while it does utilize a stack, right, the runtime stack, it is not a data structure itself. So, I should also note that if I get my way, and I probably will, this question will, this block of questions will also appear on the final exam. Something similar to this. So, which data structure is the most appropriate for a scenario? All right. So. Now this next page, so in the actual exam, this page and the next page are they're glommed together. They are glued together. It's one page with 10 points on it. And on the actual exam, instead, what happens is I give you a binary search tree and ask you to basically say node A and node B. The relationship between them, right? Node A is B's blank, right? Node C is A's blank, those kind of things. So same kind of concept, so the same terms over here. And then I ask you about how would changing the tree, right? Changing the tree in such a way would result in a full tree. Changing the tree in such a way would result in a complete tree, that kind of thing. So that's how that will appear on the test. So it does map pretty cleanly, I feel. The node at the top of the tree is called what? Yeah, the root. Okay. The links from a node to its successors are called what? Branches. Or links. Yes, the word I just used there, because those are the two canonical names for it, branches or links. So now the predecessor of a node in a tree is called what? Parent, right? But we don't actually but we almost never use the term predecessor. So parent. Nodes that have the same parent are what? Nodes that have the same parent are siblings to each other. They are technically parents, children of that same node. I mean, and you can, there's more technical terms that we use, like if we have this over here, A, B, C, D, right? A is D's what? Grandparent, that I accept that. And the more general term? Ancestor, right? I will accept grandparent or ancestor on the exam, okay? Same with grandchild or descendant, right? So long as it makes sense. Like, what is C to D? C is D's what? This isn't a term I taught, but kind of make a stab at it. Not a cousin. Cousin would be... It would be uncle, right? The other way around. Yeah, this would be the uncle node, right?
Are we going into the second and third cousins?
You could. Actually, the second, first cousins, once removed thing, once you get the hang of it, isn't too bad.
So the bonus question?
No. I don't have a hard bonus question on this one. I just have a buffer of points, and I have one give me point at the end. So describe without using code how to calculate the height of a tree recursively. So what's the height of this tree, by the way? 3. Yes, a height is 3. We know that because from the root to the bottommost leaf, there are 3 nodes in that path, right? But in the very beginning, I did mention that there's a recursive definition for height. Anybody remember it? It's way, way back. This is why I ask it as a question on the practice exam to refresh your memory. So say we're trying to calculate the height of A, right? And it doesn't really know how big it is. What it will do is that it figures out, well, how big is my left subtree? And how big is my right subtree, right? How big is its left subtree, by the way? Its left subtree is height 2, right? This subtree is height 1, right? So it knows its longest path is in its left, and it's 1 more than its left. So its height is 3. Add 1 to it. So the way you calculate your height of the tree recursively is that you get the height of your left side, you get the height of your right side. Okay? Have them calculate that. Obviously, if there's no tree or subtree, the height is 0, right? So that's your base case in recursion. So base case 0, get the height of the left, get the height of the right. Figure out which one is bigger. Right? Figure out which of left or right is bigger. By the way, is there a function that given 2 numbers will give you the bigger of the 2 numbers? You might not have used it, but there is. Any guesses as to what that might be called? Given a function that given 2 numbers will return the bigger one? Max. So specifically, math.max will return and it's one of those, it's obscure until you get told it exists, right? But math.max, given 2 numbers, will return the bigger of 2 numbers, which is pretty useful because it skips a whole if statement for you, right? So you figure out whether your left or your right is bigger, and then add 1 to it. And that's your height. Right? That's how you figure out the height of your tree recursively. This might be useful to know for the exam, by the way, if I just put it in a place where it doesn't really fit. So keep that in mind. Right? Especially if I ask you to describe how to do it recursively. So just a small hint there. Okay? Now, on the exam, I again will tell you to do this. Ask you to modify a tree. But here, we want to draw an example of each of the following types of binary trees. Use a different example for each possible for each tree. All right. So first, we want to draw a full tree. And the reason I ask you to do a different example for each one is because I quickly realized that some smart aleck could just put this as the answer for all 3 questions because this is both full, complete, and perfect. So let's go and start with full. Why is this full? Why? Yes.
Because all nodes have either no children or big two children.
Yep, every node in this tree has no children or 2 children, right? Okay? So that, I'll go ahead and just say, yeah. Okay, so this is a full tree. This is also a full tree. But if I put a node over here, it's no longer full because this node has 1 child. If I put another node over here, now all nodes have 1 child or 2 children, right? And if I do over here as well, right, all nodes have 1 children or 2 children. Full is fairly straightforward to figure out. Every node has either 1 child or 2 children. Okay. Now I'm going to skip down past complete. I'm going to do perfect first because that's a bit easier to understand. Right? Perfect has a mathematical definition, which says that given a tree of height h is perfect, right? So this is a tree of height 3. It's perfect if there are 2 to the h minus 1 nodes. The way you can kind of visually describe it, though, is that it's perfectly symmetrical and perfectly balanced, right? You know, so it is. So, you know, and notice over here it's height 3, so 2 to the 3rd, so 8 minus 1, there's 7 nodes. So for a height 4, I have to draw 2 nodes under each child over here, right? And this is height 4, and there's 15 nodes in it, right? 2 to the 4th minus 1. And then I'd have to draw 2 nodes under each of these, right? So you can visually see like why that this is a perfect tree. It's completely symmetrical. Everything's kind of just filled up, right? Every possible space is taken for a tree of height h. So a complete tree is slightly different. It says that and let me go ahead and draw a complete tree. So a complete tree says, okay, so this tree is height h, but for h minus 1, for this layer up here, for everything but the bottom layer, it's perfect, right? Everybody see how everything but the bottom layer over here is perfect? Right? Everything but the bottom layer is perfect. However, on the bottom layer, we follow a special rule. It's filled in without any gaps from left to right. Okay? So this is a complete tree. Let me give you an example of me making it not complete. I put a node over here. It is no longer complete. Why? Because we're filled in because there's a gap of 2 nodes right here. It's not filled in from the left to right. If, on the other hand, I take this node and move it over here to this node's left child, it is now complete again, right? Because it's filled in left to right. If I remove this node, it's no longer complete because it's not perfect in this layer above here, which is not really something, right? But that's fairly easy to see. So this is complete, this is complete, this is complete. If I remove this, this is no longer complete, right? Because we have a gap here from the left to right. This is complete. If I put a node here, it's no longer complete here. We have a gap here from going left to right. Everybody kind of get that concept that a complete tree has gaps in it? Oh, sorry, a complete tree doesn't have gaps, right? We avoid these gaps. Okay, and the reason we care about this is that, you know, in a heap, which use complete trees, we can map this perfectly to index 0, index 1 of an array, index 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right, without any empty slots, right? That's kind of the reason we care about complete trees. It allows us to map things to an array very cleanly without any empty slots. All right. So tree operations. Whoops. Tree operations now. Oh, and by the way, I've already uploaded last night's review of this, so that's already online for you to review. So me going over this from the class in the evening. So it's the same content, but this won't get uploaded till later. But so if you want to review it sooner, then last evening's class has it. So, all right. So here, this is a question that is exactly the same on the exam, except for the specific numbers, right? I just do different numbers on the exam, right? So this one's fairly easy. It's possible to lose a point on it just by making a careless mistake and like accidentally saying, oh, like 12. I accidentally put in 21, right? And just transposing something like that. We'll just look at that, roll our eyes, mark a point maybe or a half a point, and just move on, right? And just move on from that. If, however, you show you cannot make a binary search tree, like just because the nodes are everywhere and it's a complete mess, like we're talking like you have no idea that say that nodes are only supposed to have 2 children, right? That kind of thing. Or nodes, or basically nodes just go any which way and you just kind of just filled everything in where willy-nilly, yeah, then no credit. However, it's a fairly straightforward thing to get correct. Okay, so what we do is that we insert each node one at a time. So we start with 42, right? And then 42, then we insert 10, that goes to the left of 42. Then we insert 50, that's bigger than 42, so it goes to the right. We insert 12, so that goes to the left of 10, right? Less than, greater than. 17 is less than 42, greater than 10, greater than 12. We get to 17 over here. 80 is bigger than 42 and 50. Right, and don't worry if basically it gets a bit messy, right? And you have to like do something like this, you know, like that to get stuff out of the way, right? You're not here for art, right? You're here for computer science. So so if you have to just make things a bit messy, so long as it makes sense, right? It's perfectly fine. So 80, negative 12, less than 42, less than 10. So negative 12 goes over here, right? 100 is bigger than everything else, so it goes all the way to the right. Then 96 is bigger than everything else up to this point, right? And then, so that goes to the left over here. 96. 105 is bigger than everything we've seen so far. That was a mess. 86. Bigger, bigger, bigger. Smaller, smaller. 86, right? And now 72 for our last one. 72 goes over here, right? Bigger, bigger, smaller, empty spot. Right? So that's kind of the answer that we're looking for. Okay. Now, on the exam itself, on the actual exam, the follow-up question for this will be to do a traversal of this tree. All right? So on the exam, what I ask you to do is I ask you to do a pre-order traversal of this tree and a post-order traversal of the tree. Okay, that's what comes next on this. So why don't we go ahead and see what a pre-order traversal of this tree would look like, okay? And I think I make it a less big tree, by the way, so I don't give you so many nodes. So a pre-order traversal, what does that mean? Let's go ahead and skip to that section over here. Which of the following is a pre-order traversal of a binary search tree? B, right? Processing the new root node, then handling your left and then your right trees, right? So that is a pre-order traversal. So what would a pre-order traversal of this look like? So we start at the root. So we handle the root first, 42. Then we do our left subtree. Okay. Now to do our left subtree, we have to process 10 first. And then we process 10's left subtree, then its right subtree. Now to process the left subtree, we do negative 12. Then we do negative 12's left, done. Negative 12's right, done. We're done with negative 12, so we're done with 10's left subtree. Now we do its right subtree, 12. Then we do 12's left subtree, done. Right subtree, 17, and then 17's left and right. So we're done with that. So we're done with 42's left subtree. Now we go on to 50. We do its left subtree, we do its right subtree, its left subtree doesn't exist, right subtree. We do 80, 80, we do left, which is 72, then we do right, which is 100. We do 96, then we do 86. We're done with 96, we go to 100's right. We do 105. So we're done with 100, done with 80, done with 50, done with 42. So we're completely done. Right? Everybody follow how that works? And it's possible to just get lost in this. And that's okay. That sometimes happens. All right, so the other question is postorder. Which of these is a postorder traversal? C. Doing your left subtree and then your right subtree, then handling yourself. So here, a left subtree. Let's see. So to do postorder on this, we kind of know what's going to be last. That'll be 42. So, but anyway, so we start at 42. We have to handle 42's left subtree. To handle the left subtree, to handle 10, we have to handle 10's left subtree, which we do. We handle negative 12's left subtree, nothing. Right subtree, then negative 12. We're done with negative 12. So 10 says we got to handle my right subtree, handle the left subtree, the right subtree, 17. So now we're done with 12. Now we're done with 10. Okay. Now 42 says my left subtree is done. 50. Now we have to go into my right subtree. 50 says handle my left, handle my right. 80 says handle my left. 72. Handle my right now. 100 says handle my left. 96 says handle my left. 86. 96 says okay, handle my right. I'm done handling my right, so handle me. 100 says did my left. Now I've got to handle my right. 105. 100 says, okay, I'm done. So 80 says, oh, my left subtree and my right subtree are done. So 80 goes, I'm done. Then 50 goes, oh, my left subtree and my right subtree are done. I'm done. And then 42 goes, oh, I'm done. So sorry for jumping around the exam like that, but I figured might as well tackle that now, since that's what you'll tackle next on the exam. Okay? Okay, so now the next question will be a deletion question on the exam. Now on the practice exam, I just simply say to work with the tree you just wrote. On the was that a question? Oh no, you're just holding your hand up. On the practice, on the actual exam, I will give you a tree, and you need to delete. Basically, I tell you to delete certain items from the tree that I gave you. All right. So, using our previous answer, draw what happens to the tree when we remove the following. So we've got. So the first thing we need to remove is 42. Now 42. So there's 3 cases for when we're deleting something, right? Well, 4 cases. First, we don't find it, in which case that's boring. So that's not going to happen on the exam. So there's 3 cases you really need to concern yourself with. Right, the item we're deleting has no children, in which case we just delete it. The item we're deleting has 2 children, has 1 child, in which case we have our parent adopt our child. Okay? And finally, the case where we have 2 children. Okay, and in the case we have 2 children, we need to reduce that to an easier case. So we find the guy who's, we find our next in order predecessor, or our next in order successor, but I'm going to be going with the predecessor, for example. We find our next in order predecessor, meaning the biggest thing that is smaller than us. We find that thing, replace and swap with him, and then delete the what we just swapped into. So to find our next in order predecessor, that's kind of the trickiest. That's what I feel is like the trickiest part. For 42, he has 2 children. To find his next in order predecessor, we go 1 to the left and we go all the way to the right. That's how you find your next in order predecessor all the time. Go 1 to the left, all the way to right. If you want to find your next in order successor, the thing that is the smallest thing that is bigger than you, you go 1 to the right and all the way to the left. Don't care what you do on the exam so long as you're consistent. So we go 1 to the left, all the way to the right. That's 17. So what we do is that we take 17 and replace it over here. And then we erase the original 17. Another way to look at it is that we can swap the 2. And this is the way I would originally program this. But then I think students found it. I might go back to doing it this way next year. You swap the 2, and then you tell your left subtree to delete what you were originally deleting. Now the only reason I don't like this is because it makes your tree out of balance for just a smidge. Or makes it wrong for just a smidge. But then you tell your right subtree to delete 42. We go, oh, 42 has no children. Easy to delete. Boom. End result is still the same, though. Okay? Everybody follow that? Right? The other way you do it is you just simply swap up and delete the original. Oh, it has no children. Delete it. All right. So next thing we have to do, I'm just going to mention, what if the 17, though, did have a child over here? What do we do? In that case, we are again at the case where basically we're deleting a node with one child. So we have 12 adopt that child. Okay. So now 17. So we've got that. Delete 12. Is there any difficulty deleting 12? No, because 12 is a leaf. Now we'll delete 17. 17, we got to find the next in order predecessor. Go one to the left, go all the way to the right. That's 10. Right? We couldn't go anywhere to the right, but that doesn't matter. So 10. So this becomes 10. And we're going to delete the other 10. This other 10 has one child, so our parent will adopt that child. Right? And then 96, deleting 96. Find 96. Oh, there's 96. It has one child, so its parent adopts its child. Now, on the exam, it may be beneficial just simply for cleanliness that once you delete it, you redraw the tree just after that deletion. It's kind of the way you can show your work there. Oh, or you can give me the final answer, but depending on what numbers I randomly mashed into the tree this year, that may or may not be hard. That may or may not be easy. So, all right. Let's see. So we're done there. We're done there. Heaps. All right, so this will be on the exam, just like the tree one, almost exactly like this, but with different numbers. So long as you remember that you inserted in a complete tree, in the format of a complete tree, and everything goes basically from the top layer left to right, and then going on to the next layer left to right. So long as you remember to do that in the order and then bubble up, you'll be fine. The main thing where people lose a lot of points on this because they forget to either bubble up or they forget, hey, what does a heap look like again? And they draw this like terrible structure that doesn't make any sense. Essentially, they try drawing a binary search tree. So let's just take a look about how we would build a heap. Okay, how do we build a heap? And again, this is a min heap, meaning the smallest goes to the top. So draw a min heap. We put in 8 over here. Right, we insert that item first, 8. Then we insert 10. 10 is heavier than 8, so it stays put. Then we insert what? What's the next number, 50? Then we insert 50, that's heavy, so that stays put. Then we insert 20. That's heavier than its parent, so it stays put, right? I'm saying that things that have a higher number are heavier, so to speak. Right? 1, now that's lighter than its parent. So we need to swap with our parent, right? So that's the way a heap works. Lighter than our parent, so we swap with our parent, and then we proceed to do that until we either get to the top, or our parent's lighter than us, right? So 1 is smaller than 8, so 8 sinks down while 1 bubbles up. Make sense to everybody? Okay. And then next number, 4. Okay, insert a 4. Okay, so 4 needs to bubble up and swap with 50. And then the next number is 3. 3 is lighter than 4, so it bubbles up and swaps. Everybody kind of good on how this works? I can work through another example if you guys want me to. But I'm going to go on to the next question. If you guys want me to work through a couple more examples after this, I will. Okay. So you'll get a question almost exactly like this on the exam. I just make it actually an easier version of this. Using the heap you drew above, draw the heap after removing an element twice. So when you remove an element from the heap, what is the element you remove? The root. You always remove the root of a heap. So we need to remove 1. Now, how does removal work? Anybody remember?
Take the last element.
Yep. Take the last element and just mush it on top. and then let it, and then since that will probably be heavier than everything else, it needs to sink into the appropriate place. So right, we removed 1 by basically taking 4 and putting it on top. Now we need to let it sink down to the appropriate place. So 4 is, right, it's lighter than 8, so it doesn't need to sink down, but it's heavier than 3, so it's going to sink down that way. 4 is lighter than 50, so it stays put, right? Now to remove 3, we replace that with 50. Okay, and 50 is heavier than both 8 and 4. So in order to ensure that the heap property is maintained, we swap with our smaller child. We swap 50 with 4. Right? And now 50's hit bedrock, so it's perfectly acceptable. So this would be the answer for that one. All right, everybody clear on how that works? Does anybody want me to? Yes.
Could you go over that again?
In what regard?
Removing 3?
Removing 3? Yeah. So to remove, let's see, we removed 3 was up there, 4 was up here. 4 was down. Sorry, 4 was that. To rewind, we had 50 here. We had 4 here, right? So what happened is that to remove 3, we replace it with the last item in the heap, which is basically the last item in the complete tree slot. Basically, we remove the only item we can that would maintain the heap, the complete tree property, right? We can only remove 1 item here to make make the tree, keep the tree complete. So we put 50 up top. Now 50. Now we have to make sure reformat the heap to make sure that it remains a heap. So we swap it with the lighter of its children, right? Because it's heavier than both of them. So we swap it with 4. Make sense? Right? And suppose that basically that, let's see. Trying to think over here. Suppose that, for example, that we had that this was, instead of 10, this was 30 for the sake of argument, just because we haven't had anything that had to fall down further, and we wanted to remove 4. Suppose that this was 30, we wanted to remove 4. So we would take 4, we would replace it with 30, and now 30 is lighter than 8, so it would swap with 8. And 30 is lighter than 20, so it would also swap with 20, right? It keeps sinking until it gets to a point where it no longer needs to sink. Those previous examples, it only sunk once because of happenstance, right? And essentially, and the numbers that I banged into the exam and practice exam are essentially random, right? Because that's how I differentiate them between one semester and another. All right. So this is pretty much exactly like you'll see on the exam. This next page, just checking to make sure, this next page will also be pretty much exactly like you see on the exam. It will also be pretty much exactly like you see on the final. The only difference will be the table over here and whether whether you're encoding or decoding down here. Now, one thing I do want to note, the way I grade this, is that I don't really care. So you draw your tree up over here. It can be right or wrong, right? And you'll get points accordingly. But over here for this question, I assume the tree you drew was right? I assume that was the tree you sent to the user to encode or decode something. And then I grade that independently of this, right? So yeah, your encoding or decoding might not match mine, but it was what your tree specified, so that's what I grade you on, right? So long as you encoded and decoded properly. Now, for this question, where do students mess up? They mess up in 2 rules. The first rule is that when they dequeue from the priority queue, they forget the first thing you dequeue is always the left thing. The second thing you dequeue is always the right thing. That's the first thing. The second thing that students forget is that these things are in a priority queue, and it remains a priority queue even though you've already inserted everything into it. Right? So once you reinsert a node back into the priority queue, it reorders again, right? And that's where and that's the second place where students stumble. Okay, so let's go ahead and show how to draw this Huffman tree. Okay, let's go ahead. Oh, and this will be on the final exam. I think I mentioned that, but I want to make sure. It's always on the final exam. It's always worth like 10 points. So if you can do it here, then great. That's 10 points you'll pretty much know you can do on the final. So, that's nothing to scoff at. That's like, what, 2.5 points for your final grade? So, A appears 50 times. So let me just put this in proper order. X appears once, or whatever. You can do it in any order. You can put the letters or the numbers on the top or bottom. It doesn't really matter. Then L appears 20 times in the documents. P appears 40 times. Okay. A appears 50 times. And then E appears 60 times. And you may want to space it out so you can insert things or move things around as needed, right? Because you don't have the benefit of doing it on a whiteboard with a dry erase marker, right? You've got to do it in pencil. So, all right. So how do we draw a Huffman tree for this thing? Well, the algorithm's fairly simple. While there's more than one thing left in the priority queue, DQ once, that becomes the left thing. Okay, this is X. We'll say this is X. That becomes the left thing. DQ the right thing. Sorry, DQ the next thing. That'll become the right thing. And they become the left and right child of a new node with whose weight is the combined weight, right? X had a weight of 1. L had a weight of 20. Their combined weight is 21, right? Make sense? Right? X appears 1 time, L appears 20 times, so X and L together appear 21 times, right? So now we reinsert it into the priority queue, weight of 21. Now, however, remember it is a priority queue, so we reorder it, it jumps back to the front, right? So 21. So now we continue. 21, so this node becomes the left of a new node. P will become the right of a new node. With a combined weight of 21 plus 60, sorry, 21 plus 40, which is equal to 61. Right? And now we reinsert this into the queue, into the priority queue. And we reorder, and it stays at the end this time. Okay? I actually crafted this example so that it would work out like this. Now let's go ahead and DQ A and E. And this is the only part where this may lead to some trickiness, right? You might put A and E over here, right? Or you may put it over here, and it's hard to tell which is the right way to do it until you get to the next part of it. But that's fine. It's all relative. A and E. A goes on the left, E goes on the right. 110. They get a combined weight of 110. We reinsert that into the queue. Okay, so we DQ once. This goes on the left. This goes on the right. So if you had drawn this on over here, on the other hand, right? If you'd drawn A and E and drawn this over here, you might have gotten yourself in a bit of a pickle, and you might have had to do something like this, right? That's okay. That happens sometimes, right? So long as you keep the left, so long as the left child and the right child are the appropriate left and right child. Everybody understand what I'm saying there? So this guy will have a combined weight of, since it's the last node, it really doesn't matter, but it has a combined weight of 171. And we reinsert it into the queue. It's the only thing left, so we're done. So now to do encoding and decoding, we mark the left and right branches. 0, 0, 0. We mark all the left branches with zeros, all the right branches with ones. You don't necessarily have to do that on the exam, but I do that just simply to remind me. You don't have to mark it necessarily. Now to encode something, we need to just look at what symbol. To encode apple, we have to look at what symbols would give me A, P, P, L, E. So 1, then 0 would give me an A, right? So I'll just go ahead and say 1, 0. right? And I'll just simply draw underlines just to help me cluster them as I'm writing it down so I don't do something stupid. So P, that's 0, 1 to get to a P. And we need 2 P's, right? 0, 1, 0, 1. Now to do an L, we have to do 0, 0, 1. Right? And then finally for E, we have to do 1, 1. Okay? So that gives me apple. All right. But on the exam, I'm probably not going to ask you to encode something. Instead, what I'll do is I'll ask you to decode something. I'll ask you to decode something, and it would hopefully appear to be an English word, right? Is kind of the idea. So that way, you can kind of check to make sure that you that basically you didn't end up with gibberish.
Will we recognize the word?
Yeah, it's either like a fruit or it's love. So one of the two. So you know. Get something something pretty easy like that. Okay. Yes. All right. So, but that will give you but that will let you check to make sure that your tree was built appropriately.
No code, just all the fruit in the world.
So, let me go ahead and generate an example for decoding. Okay. So 0, 1, 1, 0, 0, 0, 1, 1, 1. Right? So let's see how decoding would work. 0, so we'd start at the root. We'd go 0, 1. That gives us a P. So this is a P. Okay? Then we'd start from here. 1, 0, 1, 0 gives me an A. 0, 0, 1, we ended at an L. 1, 1, that gives me an E. So that gets us pale. So, which is not a fruit or love. So, but I mean, it was hard to generate 2 words from this same small set. So, all right. So, but everybody see how the decoding works, right? You just follow the zeros and ones until you get to a termination point. Then you start at the beginning again. All right. All right. So now on to the coding section. So, so this first question is fairly easy, but I also happened to give it in the first time. This was an exam question the first time I taught 2168 here. So, and then I proceeded to find a question in 2017 that was absolutely awesome, and so I've used it thereafter. So let's go with, so I'm going to go ahead and open up Guinea, and I will just simply do that. First off, I'm going to delete what I did from yesterday. All right. So let's go ahead. All right, so we have public static int size tree root. Okay. So and this one says, given the root of a tree or subtree, it computes and returns the number of nodes in that tree or subtree. Now remember, root over here, it doesn't mean like the root of the tree. It doesn't mean this dot root. It means this is a node. Each node considers itself its own tree, right? Every node looks at it. The way we handle trees, because it's a recursive data structure, is that every single node is treated as the root of its own tree or subtree. So, right, if you're given a node, it looks like this, where we have the root, which may or may not be the child of somebody else, right? It may be the actual root, but it might also be, the child of somebody else. And it has a left subtree and a right subtree of just unknown quantities, right? So the only thing we can ever do is make local evaluations about this, right? So first off, what is the size of the? And it said also to forget that the size function just exists, right? You can't just return size. So the first thing, what if we're passed in a node and it's null? Well, if node if root equals null, then how big is the tree? Or its subtree? 0. So we return 0. Otherwise, well, let's figure out, well, then what I have to figure out is, then the height of the tree is, sorry, not the height, but the size of the tree is however big my left side is, however big my right side is, and then I count for 1, so add 1 to that. So I would say int left is equal to size tree root dot left. Int right is equal to size tree root dot right. And then I could return, assuming I can type right, left plus right plus 1. Right? And it's addition, so the order doesn't really matter. Right? That makes sense to everybody? So you can also do it in one line. If we decide to do it like this instead, I could return size tree root dot left, return the size of the left tree, added to the size of the right subtree, and then add 1 to the whole thing, and we're done. All right. Now what about, now it's the next question that I'm actually very thrilled with. I thought it was really good. I was actually very happy that I came up with it because kind of provides you a hint. This is a question that asks you about a kind of checking, is a tree of this certain property? Basically, it's a recursive question about a property of a tree, right? So that gives you a hint that I might ask you to solve for a tree property in the actual exam. So public static Boolean is full tree. So given a tree, it returns whether that tree is a full tree or not. And I mentioned that it's slightly different than the recursive methods we've tackled so far. So mainly because, first off, if tree, let's look at our first base case. This has multiple base cases, by the way. That's why. So first off, if tree is null, right? Is it a full tree? Is it if it's empty or not? Sure. I don't know. I don't know if an empty tree is a full tree. I'm going to go ahead and say yes, though. If it's empty, right, then all nodes have 0 children or no children, and mathematicians kind of like that definition. So this one I say I'll pass that definition on to the mathematicians, but as we're going to see, this if condition really isn't going to ever really happen. Okay? So this is if the node doesn't exist. However, if it does exist, right, what does it mean to be a full tree? I either have no children or 2 children, right? So if tree, and then if I have one child, or if I have a left child or a right child but not the other, then I'm not a full tree. If I have no children, then I am a full tree. But if I have 2 children, I have no idea whether or not I know I'm a full tree. That depends on whether my left tree is full and my right tree is full, right? So that's what we need to program. So if tree.left is empty, not tree is empty, but if tree.left is empty and tree.right is empty, right? If they're both empty, I'm done. Return true. If tree.left, if I've got a left node, but I don't have a right node, then, then that's easy to consider. It doesn't matter matter what my left tree has. I'm not a full tree because my left side doesn't, you know, my right side doesn't, you know, I only have one child, so I can't be full. Same with this one. If tree dot left is empty, but I've got something on my right, okay, then return false. So the only other case is that I have both children, in which case I can't really make a local decision. All I can say is the best I can do is this. This is the only thing I can do. I can say if my left, I'm full if my left tree is full, and my right tree is full. And we're not going to get into a weird condition, by the way, where this is where my left tree or right tree is empty. We've made sure neither of them are empty, right? So we're not going to hit that first case, really. So everybody follow this one? Yes.
So if you don't include when I practice this, I didn't include the if tree equal null, return true. I just left that out. Is that going to be a problem?
It would be a 1 point out of 12 problem or a half point problem.
Even if it's never...
Well, because the very top root could be possibly null,
okay.
right?
Yeah.
But it just, or if you put an assumption, if you put like in a comment somewhere, assume root is never null, then we assume root is ever null. We work off of whatever assumptions you give us, okay, assuming they're reasonable like that. So it wouldn't really be a problem. Your problem would be, it would be mostly correct. Although if everybody made that problem, if everybody made that mistake though, then I'd probably let it slide for everybody. But you know, I come up with a rubric and I try to adhere to it, and then I realize if it was a bad rubric, I try to adjust. All right. So there was also a practice problem as well over here, right? But I've already gone over that in a previous lecture, the equals. So over here, this is a lot like what you had your quiz on yesterday, and this is also a whole lot like what's going to be on the exam, right? So write a method which returns what characters in a string and how many times each occurs. So the difference here is that I'm going to on the actual exam, I would be you'll be dealing with a list of, I think it's a list of strings, right? As opposed to a simple string or a list of integers. So let me go ahead and delete what I had yesterday. Public static, yeah. So public static map character integer. Okay. Count string word. So basically we want to, yes?
We just assume that this is going to be like format. There will be like 2 questions on like coding trees and 1 on like maps.
Yep, that is exactly how it is. There are 2 questions on coding trees. Each question is worth 12 points on the exam, and then there's 1 question on maps, which instead of being worth 10 points, it is worth 11 points, just so I could get an even 35. Even 35. So I mean, so the but the point being is I wanted to have 35 points of coding questions on there. So we have 3 questions, and so okay. So first thing we want to do is create our. So what we're trying to say here is that given a word, we want to get the count of the characters and how often each character occurred. So like if we were given apple as our word, 1A, P appeared twice, L appeared once, and E appeared once. If we have banana, B appeared once, A appeared 3 times, N appeared twice, I think. The issue with spelling banana is you know how to start it, but you don't know how to stop it. So map character to integers, right? So we want to count characters, and so we're counting. So the key is our character, and our value is integer. And now I'll just call it map for sake of simplicity is equal to a new hash map, right? Point off if you forget that it's an interface, right? That's right. Just like on the first exam, if you accidentally did list new list, right? It's map new hash map. You can do a tree map if you want. It does not matter, right? For the sake of this problem. Okay. So we've got our method of counting. So now we need to go and check every character in our word. So there's a couple ways to do that. The way you probably know how to do it is like this. You know, for int I is equal to 0, I is less than, you know, word dot length I plus plus. But I'm here to try to tell you that you should, now that you're at data structures, you should try to use the for each loop whenever you can. And then you would go, because you'd go something like car C is equal to word dot car at I. I'm not going to do it like this because that's boring and it takes too long to type and write on an exam. Instead, what I'll do is I'll write the for each loop, which I'll say for car C in word. Well, word, unfortunately, you can't do it like that. What you do need to do is to car array. To do it like that, and that will take a word and split it up into a character array, which you can iterate over. Okay, much shorter than whatever we had to do. You don't have to worry about out of bounds issues, right? It makes it a lot more convenient. The only time you can't use it is when you have to mess with indices, right? So for every character in the word, let's go ahead and see so first off, if map dot contains key. If I've seen character C, then I want to do one. So what do I do? If I've seen the character before, well, I've seen it one more time. So let's see. How do I spell occurrences? I think it's E. Occurrences, yeah. Right? That look right? Occurrences is equal to, I got a PhD in computer science, not English, you know. So int occurrences is equal to map.get C. So this will get the number of times I've seen character C. And then I just need to update that. So map.put C, I've seen character C, occurrences, numbers of times. Great. Okay? Else, if I haven't seen it yet, oh yes, occurrences plus 1, right? Have to see it another time. It's already moving on to the next one. So if I haven't seen it yet, then what I can do is that I've seen it once, so I'll do map.put C occur and 1. And just 1. I've seen C one time. So that counts it. So notice that the main bulk of that, the work part of it, right, that's 5 lines. Map problems aren't too bad. I suppose I should remember to return this. And we're done. Yes?
That map.get,
oh.
that method, get method, it's supposed to give you the value of that key back, right?
Yes.
How is it giving you the integer back operands?
Well, our value is an integer.
Okay.
Our value is an integer, so it's returning an integer to us, right? The key is a character, the value is an integer, so it gives it back to us. So we ask for the integer that's associated with this character. So I ask, how many times have you seen A? And it will return, oh, I've seen 5 A's so far, right? And then I would go, great, you've seen 6 A's so far, right? And then when I see the next A's, I would ask, how many A's have you seen? And it would say, I've seen 6. And then you would go, great, now you've seen 7. Make sense? I also saw somebody else, and I think it was in this class. They did it something like this, which I thought was very clever, even though it had a bit of a longer runtime. It was just also another way to do it, and I figured I'd share. So first, they would say if the map doesn't have the key. So if the map does not have it, if I haven't seen it yet, then I would do a map.put the character and 0 in. So they haven't seen it yet, they put character, I've seen the character 0 times. And now, after the if statement, there's no else. They just would simply put map dot put c, and then map dot get c plus 1. So what they would do is that for what this does is that you get the number of times you've seen it, add 1 to it, and then put it back in, right? So it basically takes this block and simplifies that to 1, and not simplifies it, but it edits that down to 1 line. And then for the initialization statement over here, they put, instead of setting it up to 0, who's calling me? I think my son is trying to call me. So, how do I turn it? How do I say no? All right. So, all right. So that's that. I am sorry. This is really frustrating. Okay, there we go. All right, sorry about that. So I thought I had it turned. I thought I have no notifications turned on. So if map.contains key, put it in 0. We've seen say that we've seen it, and now add 1 to that value. So this will work. So this line works whether it's the first time or the nth time you've seen it, which is pretty useful. All right. So I'm going to skip the practice question. Yes.
Back to the thing that we just did. Do we have to use the dot put method when we update, or can we just say map.getC?
You'd have to use the put, because unlike a list, you're not modifying an object. You're replacing a value. Okay. So now let's see. So I'm going to go, so this practice question I'm going to skip over, but let me mention this is a categorization question, okay? So the difference here, and I give you the categories. So the way to solve this one is the first lines are map.put 2 new array list, map.put 3 new array list, map.put 4, not map.put 5, 4, map.put 5 new array list. So you have a line to put 2, 3, and 5, each with an empty list, essentially. And then you simply go through each of the numbers in here and ask if it's divisible by 2, put it into this list. If it's divisible by 3, put it into this list. If it's divisible by 5, put it into this list. And those are if statements, not else if statements, right? Because each one can trigger independently. A number like 15 is divisible by both 3 and 5, so it appears in both. I just want to make sure I get to the analysis part. Okay, so there will be 10 points of analysis. One question will be on hash tables, one will be on trees. So, so first off, what is a collision in a hash table? How does a collision occur? Yes?
So is it when the hash function maps
2 values? So 2 keys. Yeah, 2 keys. It happens when you try to put 2 keys in the same index. So a collision occurs when you try to put 2 keys in the same index. Right? All keys are unique, but the hash table is smaller than the space of all possible keys, because the space of all possible keys is infinite. You can put anything you want into a hash table. So as a result, if we try to put stuff into a hash table, we're going to get collisions. Hopefully you've seen the video by now that I uploaded, but the analogy is think of a parking deck, right? Think of a parking deck. If the parking deck is like 99% of the way full, it takes forever to find that last open spot. You're essentially colliding with every taken spot, so to speak. On the other hand, if it's only 50% of the way full, half the spots are open. So yeah, that spot is taken, but the next spot is open. And because people don't like parking next to each other because we're worried that we're going to, the person next to us is going to, open their doors and slam into our doors, right? We generally space out, right, and leave plenty of space so it's easy to find a space to quickly park, right? So that's the way hash tables work, and that's why they work, or that's the way that we essentially need to resolve collisions with open addressing. And this is essentially why it takes a constant time to insert into a hash table, because there's always open spots. Whenever we get too close to being filled up, we just simply build a new parking deck, so to speak. So they occur when, so again, collisions in hash tables, they occur when you get two keys. They want to go into the same index, but they can't because it's already taken, because one's already taken it. So how are they handled? Well, they are resolved by two broad categories, open addressing, and the other broad category is chaining. Now, there's other strategies that exist that we did not talk about. One is called cuckoo hashing, which works by, oh, my spot was taken. I'm kicking you out of it, and you got to go and find a new spot. And that's how so that's one strategy. But open addressing says, if my spot is taken, I'm going to go ahead and look for the next spot. Now, there's a couple ways to do that. Linear probing says the next spot, well, if they took spot I, I'm going to try to grab I plus 1. If I can't have I plus 1, I'm going to have I plus 2. If I can't have I plus 2, I'm going to have I plus 3, and so on and so forth. Next literally means the linear next one. The other way to resolve it, as I mentioned in a video, but it's not going to really ever come up on exams, on any exam, is quadratic probing, which is, oh, if I can't have spot I, I'll have I plus 1. If I can't have I plus 1, I'll have I plus 4, which is 2 squared. If I can't have I plus 4, I'll have I plus 9, 3 squared, and so on and so forth. The advantage to that is that it's more spread out. The disadvantage to that is that it takes longer to calculate because you have a multiplication operation now in there. But linear probing, but open addressing with linear probing is the way that we primarily focused on, which is simply says if my spot is taken, I'm going to go to the next one. Now the other broad way to resolve this is chaining, right? Yeah, chaining, and that just simply says that rather than having one slot, we have a bunch of slots. Rather than each slot holding one thing, it's a linked list, so we can hold a lot of things. So if I have a collision, then I just simply add on to the end of the linked list that already exists there. All right, and chaining again, just like quadratic probing, we're probably never going to see it in an exam. So now, last question. What is the worst case runtime of insertion and deletion algorithms in a binary search tree, and why? What's the worst case scenario for runtimes in a binary search tree? Yes? O of n. So why?
Because you either have all right subtrees or all left subtrees.
Yeah, you could get something that looks like a linked list. More realistically, what happens with when you got an O and n time is rather than just getting something that looks like this, right? That takes O of n time, right? You get something that looks like this. You know, something that's zigzaggy, but the big thing here is that for a linked list, for a binary search tree, the idea for this to work is that every time we go left or right, we are eliminating half the possible nodes we need to search, right? The idea is that basically if I've got a binary search tree, right, and I'm looking for the number 17, right, and the root is 50, and I've got a left subtree and a right subtree, so I'm searching for 17, I'm at the root, I go left, I don't have, if it's balanced, if this tree is balanced, then I don't have to search for any of the nodes on the right. That makes sense? I don't have to search any of these nodes here, so if this is balanced, then essentially this is half the nodes that are left, this is half the nodes. So I don't have to worry about this half. So I've eliminated half, and I'll do the same in this subtree, and then that subtree's subtree, and so on and so forth, right? And since each step essentially reduces my search space by half, it's log n time, right? Because if you remember the way I define log n time, the easy way to think of log base 2 of n is that's the number of times I can take a pile of n things and split it in half, right? So if I've got a pile of 64 things, log base 2 of that is, well, 32. I can split it in half into 32, then I can split those in half to 16, then to 8, then to 4, then to 2s, then to 1s, and I can't split it in half anymore. So I was able to split it in half 6 times, and wouldn't you know it, 2 to the 6th is 64, right? A lot more intuitive, okay? By the way, using that property, what is log base 3 of 27? 3, right? Because we can take 27 things, split it into thirds, once to get piles of 9. Then we can take those piles of 9, split them into 3s, take those piles of 3s and split them into 1s. Can't split it anymore, right? So log base 3 would be basically, you know, I'd reduce the search space to a third, or by 2/3 each step of the way. All right. So, and that's all the questions on the exam. Now there will be 15 pages, but a lot of the pages will be like, you know, plenty of space for you to work on. There's actually more pages on the practice exam that actually have content than on the actual exam. For instance, the last 2 pages, the last page is just simply your give me point, and then there's also just a page 14 doesn't have any content on it, just simply so that it's a blank piece of paper. And then your first 2 pages, of course, don't have anything really on them either. They're just your totals, right, and stuff. So that's what I got for you.